This chapter is all about intramolecular and intermolecular interactions, leading into a detailed discussion about hydrogen bonding. So let's now take a look at these different types of interactions. Once we go through an overview of these types of forces, we'll be able to see how we can categorize hydrogen bonding, whether it's intra or intermolecular, and then go through a bunch of examples and applications of just how important hydrogen bonding is to literally everything on the molecular scale. So in this lecture, we're first going to do a quick recap of the previous topic, basically things we want to bring into this lecture, specifically the law of increase of entropy and how to model the size of a polymer. Then we're going to move on to the main part of the lecture. So we want to look at the differences between intra and intermolecular interactions. And then we want to take a look at hydrogen bonding. So that will make up the brunt of this main lecture. And in turn, we're going to, well, specifically when we look at hydrogen bonding, which we call H bonding, we'll be looking at the geometry of hydrogen bonding, as well as trying to predict their multiplicity. And then in turn, take a look at hydrophobicity to see how that changes things. So once we know how to model hydrogen bonding, then we'll be able to use this to make predictions about how different molecules are going to interact with each other in water and where we could potentially use this in modeling different macromolecules. So let's first do a quick recap of relevant topics here. Last class we talked about the law of increase of entropy. In other words, any closed system is going to tend towards a state of higher entropy. So we call this an arrow of time. And on that same note, we can assume that if there's a bunch of particles in an invisible box, over time the particles are going to tend towards a higher state of disorder, so they're going to become more distributed over time and supposedly expand the box as it becomes more disordered. So remember we had our entropy equation here, where S is equal to kb ln of W, where W represented multiplicity. So in most cases, we won't even need to use this part. We would just have to focus on the W and being able to observe what that value would be. So in this lecture, once we talk about hydrogen bonding and the spatial geometries of hydrogen bonding, we'll be directly observing what W is equal to versus calculating it through the factorial expression. So we'll be going through examples at the end of this lecture to help familiarize you with how to apply this equation. So last lecture, apart from looking at the equation for entropy, we also looked at how polymers could be considered beads on a string. So if we have 14 beads, so there would be 14 of these here, we can ask ourselves, how many possible ways would we be able to arrange these 14 beads? So right now we can arrange them like this, like that, or like this. So there's 3 different ways, but as you can imagine, if we're looking at this in 3D space, there are so many different configurations that you could use to represent this polymer. So I would say there's pretty much countless ways to rearrange these 14 beads in 3D space, but there's something we haven't introduced yet to help narrow down our choice. And that missing component is intermolecular interactions and hydrogen bonding. So for example, if there were if there was a preferred attraction between number 1 and number 14 over here, then it limits the number of configurations we could have for this polymer. And that's something we'll be talking about in later lectures when we look at protein binding and folding. So once we figure out how intermolecular interactions and hydrogen bonding can affect the different configurations of our macromolecules, we can then move on to the energetics or the energy involved with each different configuration. So that's kind of the structure of the class. We first have to introduce models to everybody, then we have to introduce more and more factors. So in this class, we're introducing intermolecular interactions, and then in the future in the next class, we're going to introduce energy. So before we can even model interactions, we have to understand them. And there are two different types of molecular interactions. There's intramolecular interactions for within molecules, just like chemical bonds. And there's also intermolecular interactions for between molecules, like weak interactions at a distance. When we look at hydrogen bonding, it's actually a combination of both, so we'll go through that as well. So why don't we start off with intramolecular forces? It's basically a force that binds atoms together to make a molecule or a compound. There are ionic bonds, covalent bonds, and metallic bonds. So if you've taken some basic chemistry courses, you'll probably have gone over these before, but I'll go through them briefly as well for those who aren't as familiar. So we also have intermolecular forces, and those are forces that are present between two molecules or atoms that aren't bonded. So basically you're looking at two molecules interacting with each other versus the molecule itself. So because they're forces between molecules, it makes sense that they would be weaker than intramolecular forces, because those are the forces that hold the molecules together as one piece. So intermolecular forces in general are going to be weaker than intramolecular forces. Of the intermolecular forces, hydrogen bonding is the strongest, and that's the one we're saving for the last because that's pretty much all we want to care about. So we also have ionic bonding, or ionic bonds. We have dipole forces and van der Waals forces. So things you would have learned in Physics 280 if you have taken that or are taking it. And if not, that's okay. We'll go through everything as well. So keep in mind, we won't really be focusing too much on these forces per se, but rather hydrogen bonding. It's the most important for this course. But just like all things, I have to go through every single type of bond just so that you can familiarize yourself with the content and understand where all of it comes from. So now we want to figure out why these types of forces are important. So for intramolecular forces, we call these strong forces. Chemical bonds are considered intramolecular forces, and we can measure bond enthalpies, bond strength, to determine the chemical properties of a specific structure. Meanwhile, intermolecular forces are a lot weaker, but they're extremely crucial because they can help determine the physical properties of molecules, such as boiling points, melting points, densities, enthalpy of fusion, etc. So it's important that we understand that both play a key role in all of this. So why don't we take a look now at intramolecular forces, specifically chemical bonds. So chemical bonds would be ionic bonds or covalent bonds. And then we're going to briefly touch on the hydrogen bond, and that's going to lead us to a discussion of intermolecular forces. So first of all, I have to start off with the anatomy of an atom. This course has a lot of students coming from different walks of life and different fields of study. So I have to briefly introduce what an atom is, as well as its electrons, so that we can look at modeling in different ways. So as an example, I just wanted to go through the carbon atom and the hydrogen atom and specifically look at their valence electrons. What this valence electron means is that there's going to be an outermost shell for each of our atoms. So if I have carbon here, I take a look at the atomic number, it's 6. It means that there are 6 protons and 6 electrons, and that means that the first shell only has 2 spots. 2 electrons are going to be used up to fill up that shell, and then the remaining 4 are going to go in the valence shell. So the valence shell basically means the outermost shell, and if it's not complete, then that means that your atom or your element is a reactive species. So in this case, carbon has 4 electrons in the outermost shell, and there's 4 spots left. With the hydrogen atom, the atomic number is 1, which means that there's only one electron, and it only fills in the first shell, which is also the outermost shell. And that spot holds 2, so there's one missing electron here, or one open spot. So when we think of interactions and chemical bonds, we have to consider the interactions of the outermost electrons. In other words, the electrons in the valence shell. So we can take a look at this chart here to determine how many electrons are in the outermost shell for each element. So there are a couple of important trends here. Over here in yellow, these are called inert gases. So that's helium, neon, and argon. And you'll see that there are no red dots. The red dots basically mean electrons that are in an unfilled valence shell. If it's all grayed out, it means that that element is happy. All of its shells are filled with electrons to the max. And that means it's going to be chemically unreactive. So these are very stable inert gases. So in red, you have all of these elements, and their outermost shells are not full yet and can participate in reactions with other atoms or molecules. The whole goal with this is to try and make each of these elements happy. So to be happy, they want to have a full valence shell. So for example, if I look at sodium and chlorine here, sodium still has 7 spots left to fill up its valence shell, whereas chlorine has 1. If sodium chooses to donate or somehow share its electron with chlorine, then technically chlorine can get its full valence shell here for shell number 3, and sodium can drop back down to a full valence shell for the second layer. So it's these types of interactions that we can use to predict how different elements are going to interact with each other. So these trends are important to know when modeling, because essentially when it comes to modeling, this isn't a chemistry course, but what we can do when we take a look at these is consider argon, neon, and helium as unreactive species. We can label them N for non-reactive, and the rest of them, they are reactive, so we can label them R for reactive. That's just an example of a crude model where you can just categorize elements into reactive or non-reactive species. So now it's time to take a look at what chemical bonds there can be. The first one I want to talk about is the ionic bond. These ionic bonds are formed when electrons are transferred from one atom to another. So this example on the left is with hydrogen, with their 1 electron in their valence shell. And so we see hydrogen passing on one electron over to another atom. But why? It's because each atom wants a full valence shell. So if the atom is missing 1 electron to become inert, it's going to take one from another atom. And for example, if the atom is missing 1 electron to become inert, or if the atom only has 1 electron and 7 empty spots, like sodium, then most likely sodium is going to give its electron away to reach a lower level of fulfillment. So we're going to take a closer look at our example for sodium chloride, or NaCl. If we take a look at the previous chart, we notice that sodium has 1 electron, while chlorine has 7 electrons in their valence shells. So with the goal to have complete valence shells, it's most probable that sodium will donate its electron to chlorine so that chlorine can have 8 electrons in total and fulfill its valence shell. But some important things to note: when an electron jumps from sodium to chlorine, just like this example, both atoms are going to become charged. So if the atom loses an electron, it's going to become positively charged, and then we have a positive ion. And then the other one that receives the electron is going to become negatively charged. So in that case, one becomes positive, one becomes a negative ion, and that means these two charged ions are going to be electrostatically attracted to form an ionic bond. Taking a closer look at our example, the product of the reaction between sodium and chlorine is crystalline sodium chloride. So basically it contains sodium and chlorine ions packed closely together in a regular array. In this structure, charges are exactly and perfectly balanced, and that basically gives us table salt. So we're going to be looking at table salt a little bit later once we talk about hydrogen bonding and why it dissolves in water. It would be good to know why, because that might pop up in a future assignment. So what about covalent bonds? We talked about ionic bonds where basically there's a transfer of electrons, but with covalent bonds, there's a sharing of electrons. So these are formed when electrons are shared between two or more atoms. Why? Because when they share them, they both become inert and have full valence shells. So an example is given here. Once again, you have hydrogen with one electron in its outermost shell. So here, if hydrogen wants to have a full valence shell, the other option is for it to share electrons. So when shared, that means two electrons are going to participate in a bond, and that means they both have to be somewhat close to each other in order for this to happen. So there's going to be some sort of bond length between the two nuclei that would be determined by preferable and optimized attractive and repulsive forces. Continuing on, we can consider a molecule to be a cluster of atoms that are held together by covalent bonds. So as we progress through the course, we'll slowly come to see that we worry more about covalent bonds and of course hydrogen bonds. So now let's take a look at an example of a covalent bond between two hydrogen atoms. So we know that each hydrogen atom has one electron in its valence shell. So each hydrogen atom is not satisfied, and they're either going to want to lose or take an electron. But they only have each other, so instead of transferring, because they basically can't give another electron away, instead of transferring, they can both satisfy their valence shell requirements by sharing an electron with each other. And there are three options here. There's basically no attraction with this middle one, so there's no way they can share their electrons. With this one, the two hydrogen atoms come really close to each other, but their two positively charged nuclei are going to repel, and that does not bode well for electrostatics. So in this case, there has to be some sort of optimal length where the nuclei are not going to repel each other too much, yet still be attracted to each other so that the electrons can be shared. This optimal bond length has already been shown to be 0.074 nanometers for the hydrogen molecule. But something else I haven't mentioned is when we look at covalent bonds, there can actually be more than one covalent bond per molecule. So how can we even determine how many bonds there will be? So we basically have to look at the number of missing electrons in the valence shell. So for example, carbon has 4 missing electrons, nitrogen has 3, oxygen has 2. So if I take a look at carbon, again, there's 4 present electrons and there's 4 missing electrons. This means that carbon can technically have up to 4 electrons shared with it, whether that comes from 4 different atoms or just another atom that shares 4 electrons at once. So why don't we take a closer look at that? Let's assume that we have carbon and carbon wants 4 more electrons. Couldn't we get 4 hydrogens and get them to share 1 electron with carbon each? In this case, you would have C in the middle and then have 4 H's attached to it. So what does this mean? Carbon would then be satisfied, right? So it now has 8 total electrons, but how about hydrogen? If hydrogen shares one of its electrons with carbon, then it still needs one more electron so that it can be satisfied. So it's a mutually beneficial relationship. Hydrogen shares one of its electrons. Carbon also has to share one of its electrons. So because carbon has 4 electrons present and it's missing 4 electrons, then 4 hydrogen atoms can come in and form single covalent bonds with carbon. In other words, 2 electrons are going to form one covalent bond between carbon and 1 hydrogen. So let's go through an example. And I know these examples slowly build up to where I want to lead you. We're going to slowly move into spatial geometry of all these bonds, which will come in very handy later on for hydrogen bonding. So with carbon, we know that there are 6 electrons in total, and that means there's 4 electrons in the outermost shell. And that means we're going to have to bring in a hydrogen to share one of its electrons for each of these 4 empty spots. So we can then represent this using a structural diagram where carbon is single bonded to 4 hydrogen atoms. So I've brought in 4 different hydrogens, and carbon is now attached or covalently bonded to 4 different hydrogens. This molecule is called CH4 or methane, but although we know this is what it looks like, and also you've probably studied this in previous courses before, I want to take a closer look at CH4. So as you can see, when hydrogen covalently bonds with carbon, hydrogen is actually offering up 1 electron, while carbon offers up 1 of its electrons to complete hydrogen's valence shell. So as I've mentioned before, 2 electrons are in 1 bond, and that's important because the electrons are going to be in pairs. And because of these, we can then look at the spatial geometry of covalent bonds and molecular structures. So even though we just went through some basic chemistry, it's all for a purpose because now we want to take a look at what geometric shapes we can use to model different molecules with, and it's all due to these types of bonds that can be formed. So depending on the number of covalent bonds that you have in your molecule, they're going to be oriented differently. So looking at the images in the top row, we have oxygen with 2 covalent bonds, 1 on each side. We also have, if we add 2 hydrogens, we get H2O like this, and that forms a V shape because of a 109-degree bond angle for oxygen. For nitrogen, we see 3 bonds, and that means that the bonds have to be oriented at electrostatically optimized distances from each other. So there's going to be specific angles that these are perfectly balanced with each other. Finally, we can look at carbon. So remember, carbon can form up to 4 covalent bonds, and that forms a tetrahedral shape. The one thing I haven't really mentioned are these lone pairs. So with oxygen here, there's actually 2 lone pairs of electrons here and here that you don't see, whereas nitrogen also has 1 lone pair over here. So with carbon, you can see a tetrahedral shape, but technically each of these could be a tetrahedral shape as well if you also consider the lone pairs that are invisible right here. So these molecules formed by oxygen, nitrogen, and carbon have been studied so much that they have a precise 3D structure that's defined by bond angles and bond lengths. So these have been studied before, and these are the types of information, for example, 109 degrees, different bond angles, bond lengths. These are the values that we can use when we're modeling things. So we now know that there are bonds and that there can be more than one bond per atom that leads to different spatial geometries of molecules. But what about bond strengths? So if we've looked at the number of bonds, then the strength of the bonds would most likely be related to either how many electrons are in one bond, or maybe how much strength is required to break the bond. So we're going to define the bond strength as the amount of energy that has to be supplied to break a covalent or non-covalent bond. And this is expressed in units of kilocalories per mole or kilojoules per mole. So 1 kilocalorie is the amount of energy needed to raise the temperature of 1 liter of water by 1 degree Celsius, and we equate 1 kilocalorie to 4.2 kilojoules. So these are just values that, once again, if you're ever asked a question where you have to convert different values, or if you're asked to calculate something, these are conversions and known values that you can use immediately. Moving on, we want to ask another question. Why are covalent bonds so strong? In fact, they're stronger than ionic bonds. So why would that be? For various reasons. Number one, they become inert as their outer valence is completely filled. So by inert, it means that they're not positively charged or negatively charged like positive and negative ions with ionic bonds. That means they won't be as reactive or break spontaneously at room temperature. So if you have ions, when you put them into water, they're going to separate very easily, but not with covalent bonds because they're inert. And most importantly, covalent bonds are responsible for the formation of small and large molecules. So they're super, super important. On the same topic of covalent bonds and strengths, I also hinted at the idea that there could be more than 2 electrons in a covalent bond, and that's true. So this actually plays a critical role in how flexible a bond can be. So taking a look at these two diagrams here, at the top, this is ethane with a single bond. So if we have a single bond, where one electron is shared from each atom or molecule, basically the assumption is that each side can swivel around this single bond, so there's a high degree of flexibility. But if we have a double bond, that's when 2 electrons are shared from each atom or molecule, so a total of 4 electrons are going to be in this double bond. As you can see, it looks like there's one bond here and one bond here. It means it's not going to be as flexible. So if we have 2 single bonds together, this whole molecule is just going to become stiff. Instead of rotating, we deem it a planar molecule. And these double bonds are going to play a significant role in determining the 3D shapes of different macromolecules, as we'll see later on in the course. So definitely remember that the orientation and also the different possible configurations of molecules are going to be affected by whether you have a single bond or a double bond. So here's a good example. When we talk about multiplicity, as we'll do later on in this lecture, multiplicity basically means how many different ways can you configure this molecule. If I take a look at this, there's many different ways because I can spin the molecule on the left 360 degrees, same with the one on the right, 360 degrees. So there are going to be twice as many combinations or configurations possible. But once I switch to a planar molecule or a double bond, I'm going to only have one possibility for this link. So in that case, your multiplicity goes from many to very few. So that's going to help us in calculating the entropy involved and also which structures are more preferable. So we've covered the covalent bond in some detail, but now it's time to look at electrostatics. So although we know that the covalent bonds can form between atoms, we want to ask if there are preferences as to which atoms are going to bond to each other. So different atoms are going to be attracted to each other to different degrees. Carbon, nitrogen, and oxygen atoms attract electrons strongly, while the hydrogen atom is weak. So looking at this structure for the water molecule, we can consider a polar structure as one that has, number 1, a positively charged end, and number 2, a negatively charged end. So with this example of a water molecule, we can see that oxygen is more electronegative because it's going to attract electrons more strongly. So we have an electronegative region in the red area here, and we have an electropositive region in the white area here. So the symbol delta just represents a partial charge. So there's a partial positive charge here at the hydrogens and a partial negative charge at the oxygen. So then, what is a polar covalent bond? One of these. A polar covalent bond is a covalent bond that shares electrons unequally. So there's going to be more electrons on one side than the other side. And that's where this uneven charge distribution comes from. So taking a closer look at water and its covalent bonds between oxygen and hydrogen, we have a similar diagram. This time we have oxygen with 6 valence electrons and 2 empty spots. So we bring in 2 hydrogens to form covalent bonds. That means hydrogen is going to offer up 1 electron and oxygen is going to offer up 1 electron as well. So then you get these 2 covalent bonds between oxygen and hydrogen, where there's 2 electrons for each bond. The remaining 4 electrons are going to group together in a set of 2 lone pairs. And in this case, we can kind of see a tetrahedral shape. There's 1, 2, 3, 4 sides to this. And it's good to remember that there are 4 sides with 1 electronegative region and 2 electropositive regions. Another thing I wanted to mention was that these 2 bonds here form a V shape, and that V shape is 109 degrees. So with all our talk about covalent bonds and polarity, this leads us to the hydrogen bond. So we can finally talk about the hydrogen bond after all of our discussions and the introduction of intermolecular forces. We know that the water molecule here is a permanent dipole. That means it contains covalent bonds connecting atoms together, and there's an electropositive region with the hydrogens and an electronegative region with the oxygen. That also means that it can attract and repel other molecules depending on their orientation. So if you put a bunch of water molecules together in a solution, they can be connected by what we call hydrogen bonds. So there was hydrogen bonding intramolecularly, but now we also have intermolecular hydrogen bonds here. And this is something we'll focus a lot on after we finish our discussion of intermolecular forces and interactions. So we're not quite there yet, but we can finally see a connection from covalent bonds to hydrogen bonds. So we've covered intramolecular forces. Now we want to cover intermolecular forces. So hydrogen bonding is one of them, but it's so special we're dedicating an entire section or 2 to it. So here we're just going to go through some weak interactions that you've probably seen before, and the only reason I want to show them is because we can model them, and there are already very well-known models for those. So I'm going to quickly go through them because they're really not the focus of this course, but it's still good to know that they're there anyways. Keep in mind There's a lot of these intermolecular forces, and they can be represented by electrostatic equations. So I'm just going to be presenting them here as examples of all of the efforts that other biophysicists and theorists have done to model them. So if you've taken Physics 280, this will be really familiar to you. If not, then hopefully you can appreciate all the different interactions between different types of molecules. So the first one we want to look at is the Coulomb force, or the electrical force between charged particles. So we can use Coulomb's law to model this, where we take each molecule or particle as a point source with a charge little q or big Q, and you just apply Coulomb's law. They're a distance r apart, and we have the electrostatic force being kqq over r squared. In this case, k is equal to 1 over 4 pi epsilon naught, and then we've introduced an additional term, epsilon r, as a factor because it's in water and it's experiencing some sort of hydrophobic force. So that's a constant. You can also calculate the approximate potential energy just by taking away an r. So this is the simplest one that we can use a model for. So basically using Coulomb's law to model the Coulomb force between two permanently charged particles. I also wanted to mention that there's some sort of length LB called the Bajerem length in water. So it would be a good thing to remember what the Bajerem length is, because we will get back to it in the future, not in a lot of detail, but it's very similar to something you've seen before, which is called the persistence length. So there's all these different types of lengths that are known for either different solvents or different molecules. And in this case, the Bajerem length is 7 angstroms. And what it means is that at this length, the energy is equal to kBT. So it's the Boltzmann constant times the room temperature, and you get about 0.6 kilocalories per mole. So the Bajerem length is the length, or R, between the charges that's going to allow for this energy to be 0.6. So the only reason I bring this up is because for different fields of study, you're going to get different parameters that are known. So like I explained before, when we were modeling the physical size of viral DNA, we had the persistence length. Now we have the Bajerem length to refer to the separation between two elementary charges that give us 0.6 kilocalories per mole of energy. So there are certain parameters that we can use to make life easier for us when we use our models. Moving on, we have charge dipole interactions that occur in the presence of an atom with a formal net charge. So this is one with a formal net charge and one with a dipole. So we can model the electric potential energy using this equation. I won't talk about it in detail, but basically there's the introduction of vector quantities. That's because this dipole is kind of on a slant. It means that we have different charges at different points on the shape at different distances away. So that means you're going to have to consider all of the different contributions of charge to the net charge here in order to calculate the total energy. That's not the only option we have. Even though I have this dipole on a slant and a charge, what happens if my dipole is turning or spinning? So in this case, if we have a rotating dipole, to complicate things even further, you're going to have to calculate the energy for each angle and get an average value, which turns out to be this. So luckily we don't have to calculate or derive this. I don't want to go through it, but I rather want to present this model because they've been created and have been favorably accepted for us to make predictions with. So keep in mind this E is just the average value of all of the energies calculated for each direction of the dipole. So the dipole could be here for one of the calculations, straight up or backwards, and then you just sum it all up. So it's still not all the options. We've taken a look at one net charge or one permanent charge and one dipole. Now we have to take a look at two dipoles. So if you have two dipoles, the model becomes a lot longer and a lot worse, just because there are so many more parameters. First, you have different charge contributions from different areas on this dipole. Same over here with the dipole on the right. So you're going to have two different position vectors as well as different distances for each of them. To make things even more complicated, you can also have these two rotating. So if both of them are rotating, you can average up all of the interactions, and luckily you can actually cancel out some terms and end up with a generally accepted model for the average energy between two rotating dipoles. So all of this looks pretty daunting if you were to do calculations or manual calculations, but with software nowadays, if you have simulations, simulating software or anything like that, modeling this becomes a breeze. There are still a few more to look at. Here we have a charge and a charge-induced dipole. So the idea is that a charged molecule, Q, is going to interact with another molecule that was normally neutral or originally neutral, but was induced with a charge. So we can model this too, but it gets a little bit more difficult. So the models are more like major approximations. The only thing we can do is say that the energy is proportional to this term. So as you can see, the more and more temporary the forces become, the more and more these models become major approximations or major oversimplifications. So how else can we change this scenario? We can swap this charge with a dipole to get this. So we can have this. And then we have another equation for the potential energy that's experienced on either side. But there's also one more we're missing, and the last one, that's if you have two induced dipoles. From whatever sources, it doesn't matter. If you have two induced dipoles, we call this London dispersion force, because there are two transient dipoles or two quantum dipoles that arise from quantum fluctuations. So essentially, these London dispersion forces are going to be the weakest intermolecular forces because they are truly temporary forces between temporary dipoles. So they're as temporary as you can get. There are some models that you can use to try and predict either the forces experienced for each of these induced dipoles or the energy involved, but they are major approximations. And finally, we have van der Waals forces. And I pose that as a question because in Physics 280 or in other courses, I think there might be a little bit of confusion with this. I've taught this before, and there are quite a bit of students who are unsure how to categorize things. So van der Waals forces actually aren't forces themselves. It's a general term that's used to define the attraction of intermolecular forces between molecules. So there's essentially two kinds of van der Waals forces, and we've already covered them all. So there are dipole-dipole forces, and then there's also weaker dispersion forces with induced dipoles. So apart from being able to recognize these types of forces, their names, and how they're different from each other, that's the extent of what you would have to know about it for this course. Like I said, it's there because I have to go through what types of forces there are. and that there are models for these if you're interested. But our focus is going to be on hydrogen bonds and interactions within water. Why is that? It's because if you think about macromolecules, proteins are going to be in solution, lipids are always in solution, and also nucleic acids like DNA, they're also in solution. And whenever something is in solution, they're going to have to interact with water, and water is going to be hydrogen bonded with itself in what's called a hydrogen bonded network. So that's why hydrogen bonding is absolutely crucial for not just this chapter, but every single chapter afterwards, because macromolecules have everything to do with hydrogen bonding. So finally, we've reached hydrogen bonds, and we can finally take a look at it. In order to truly appreciate hydrogen bonds, we have to go through the structure of water and how we can treat water as a molecule and also as a solvent. And that's absolutely crucial to know that water can interact with it, with other water molecules within a solvent. So what exactly is a hydrogen bond? We can finally start our discussion for H bonding. It's basically an electrostatic force of attraction between, number one, a hydrogen atom that's covalently bound to a more electronegative group, and number two, another electronegative atom that bears a lone pair of electrons. So basically, a hydrogen bond arises from when there's an electrostatically positive region and an electrostatically negative region of a molecule. Hydrogen bonds can be intermolecular or intramolecular. So intermolecular basically means between separate molecules. Intramolecular hydrogen bonding occurs within the same molecule. So if we take a look at ethylene glycol here, it has two hydroxyl groups, and these hydroxyl groups have uneven charge distributions and electronegativity. So when they approach each other, they're going to create a hydrogen bond, and that is intramolecular. So now let's take a look at hydrogen bonding in water, which means we're now looking at hydrogen bonding as an intermolecular force. That's the main thing we're going to be looking at. So hydrogen bonds can be formed between two adjacent water molecules. So looking at this picture here, we have two water molecules, and we can see that the electronegative region is attracted to the electropositive region, and that's where that hydrogen bond is. So they're polarized, they're attracted to each other, and that attraction is very strong. Another thing about the strength of hydrogen bonds is that they're going to be the strongest when they're linear, which means you want to orient the molecules so that the hydrogen bond is directly in a straight line from the two different regions. So hydrogen bonds are the strongest weak interaction bond at about 1/20th of the strength of a covalent bond. Something to remember here is that the hydrogen bond length is known to be 0.17 nanometers, whereas the covalent bond length between hydrogen and oxygen is 0.10 nanometers. So just how close and comparable these numbers are show you how strong hydrogen bonds can be. So we've taken a look at the hydrogen bond. We now want to take a look at the water molecule. So the water molecule itself is neutral, so it has a net neutral charge. But because of the asymmetrical distribution of electrons, water becomes a polar molecule. So the oxygen here has two lone pairs of electrons. It's going to draw electrons away from the hydrogen nuclei. So H takes on positive charges at these two ends, and then you have the oxygen becoming slightly negative. So this means if you take a look at the water molecule here, there's an electropositive region and an electronegative region, which I've mentioned quite a few times, with the O over here representing the electronegative. So this is extremely important for hydrogen bonding. The reason why I'm repeating it so much is because all we really care about is where it's electronegative and electropositive. So why don't we take a look at what happens when we have several water molecules together? So here, with several water molecules, it's expected that the electropositive regions are going to be attracted to neighboring electronegative regions. So you have the white hydrogens, which are supposed to be positive, being attracted to the negative O's, or oxygens. And if I take a look closely, I can see my central molecule here, there's an oxygen and two hydrogens, but there's also two lone pairs. So technically it forms 1, 2, 3, 4, a tetrahedral shape. That tetrahedral shape is extremely important for some future lectures, not future slides that we're going to go through. So because of this tetrahedral bonding, this creates what we call a hydrogen bonded network of water molecules. It's very important to understand because this network is always fluid and always changing. At any given point in time, it's not going to be 100% of these water molecules that are going to be hydrogen bonded to each other. It's actually about 2/3 that are constantly hydrogen bonded. So at any one time, hydrogen bonds are going to form and they're also going to break. So they are intermolecular forces and considered strong, but also weak and breakable interactions. So water's always fluid, it's always moving. Your water molecules are always bouncing around in water. So it makes sense that it's not always tied together in a network, or else it'd be a lot more viscous than we know. So it's this flexibility in breaking and reforming these hydrogen bonds, this cohesion, that allows for water's unique properties, such as number 1, high surface tension, specific heat, and heat of vaporization. So we're now going to take a closer look at the hydrogen bonded network and how we can predict different configurations of water molecules. So on the graph to the left, it shows the percentage of molecules that are hydrogen bonded at specific temperatures. And this is a trend that you can probably predict yourself. The higher the temperature, the fewer the molecules that are hydrogen bound. So we can expect more breaking to occur with higher temperatures because there's going to be a faster movement of molecules. That totally makes sense. To the right, we also see a graph representing the number of hydrogen bonds that the water molecules experience in the hydrogen bonded network. In other words, do the water molecules form 0, 1, 2, 3, or 4 hydrogen bonds with its neighbors? So going back up, does it form 0, 1, 2, 3, or a total of 4 different bonds? So it seems like the most probable answer is 2 or 3. So every water molecule is usually hydrogen bonded to 2 or 3 water molecules in the hydrogen bonding network. So this data has been obtained through computer simulations that have been made possible from various data from, I believe, Raman spectroscopy. So different experiments can give different types of information, and from that information we can create models to help guide future predictions. Now it's time to take a look at the spatial geometry of bonding. And if you remember, we took a look at spatial geometry within molecules before with the covalent bond. So remember, carbon was carbon had bonded to hydrogen 4 times. But now we want to take a look at spatial geometry for intermolecular bonds, or hydrogen bonds in this case. So where carbon had that tetrahedral shape, we can also use the same assumption for the hydrogen bonding network and assume that there's a center or central water molecule that we can see somewhere here in the middle of this tetrahedron. And there are also 1, 2, 3, 4 possible interactions that it can have. So here, we actually want to assume from the V shape of water molecules. So something like this. I don't have much of a demo at home, but I bought a chemistry set from U of Waterloo years ago, and this is the first time I'm using it. So I swear it finally comes in handy after 10 years. Basically, you have your oxygen here, and you have your 2 hydrogens, which are not positively charged, but they're electropositive. And the idea is, pretend there's some imaginary tetrahedron around this. Now I'm trying to figure out in which direction or in which configurations this water molecule can be. So if I have the top, so if you can see this right here, if this is the top over here, and I have another water molecule here, and one at the back, let's say, then my hydrogens, being electropositive, are probably going to point upwards. So for example, in this case, one's going to want to point upwards towards the electronegative region, and the other's going to want to point towards the other corner where you have an electronegative oxygen. But that's not the only configuration I have. I can have it this way. I can have it this way for the other one that's here, the other oxygen. I can have it like this for the oxygen behind. I can also have it facing downwards, or like this, or like this. So basically, as long as there are favorable interactions for these 2 hydrogen molecules or hydrogen atoms, and there's an attraction between positive and negative, then that can guide us in terms of what types of configurations the central water molecule can have. So we're going to go through a few more examples. It's a little bit difficult to explain without a chalkboard and everything, but I will do my best. And of course, if you have any questions, feel free to send me an email and join the live lecture so that I can go through an example with you. So we ask ourselves now, why is this possible? So oxygen, like for example, we want to answer why it's possible for the tetrahedral bonding to occur. So oxygen is bound to 2 hydrogens and 2 lone pairs of electrons. I've been hinting at this the whole time, but if you count the 2 lone pairs of electrons, you can form a tetrahedral shape. So together, the 4 pieces can be separated equally, and that forms a tetrahedron, which means there's 4 different types of interactions that can happen. So how many hydrogen bonds can water form with other water molecules? Up to 4. That is the answer. But a better question is, how many ways can it form these hydrogen bonds? So of course, this is a course about modeling, so we have to find ways of being able to represent the orientation of the water molecule. So basically this that we were looking at. So if we know that there are a maximum of 4 possible hydrogen bonds, that's still not enough. It doesn't help us whatsoever when it comes to modeling and predicting what's the most probable configuration. So we want to know how water molecules are going to be oriented with respect to each other. And that's why we have to look at multiplicity. So we've talked about multiplicity already, and now it becomes very important. So we're going to redefine multiplicity in this case to be more specific to what we're studying. We'll say that multiplicity, W, is now the total number of fully hydrogen bonded configurations of the central water molecule. So basically, how many different ways can I orient this along the tetrahedral shape while having it still enjoy favorable interactions? So we're assuming the central water molecule already has 4 hydrogen bonds. But how many ways can we orient it so that the electrostatics are preferable and possible? If we take a look at the example here on the right, the answer is actually 6. So try and think about why it would be 6. And it really has to do with looking at all of the corners of the tetrahedral shape. So we note that all the corners are red, but all of these corners, all they're representing are just other water molecules. So if this is my central water molecule, there's an electronegative region here. It means that, let me change to a pen. Okay, so couldn't see my pen here. So in blue, I've kind of drawn this tiny little blue dot here, and that means it's going to have some sort of interaction with this water molecule, and then there's also going to be your lone pair of electrons interacting with this molecule. Oops. So essentially what it's saying is that when I have a central water molecule, there's going to be a positive region here, and it's going to have a preferential interaction with the negatively charged region of another water molecule. So that's one option. The other hydrogen can have preferable interactions with a negatively charged region here. But the 2 blue lines I drew before, the only 2 options left are the lone pairs of electrons. So that means this water molecule should be oriented so that its hydrogen is facing towards the central water molecule. So because I'm looking at polar, or basically hydrophilic substances, at each of these corners, it means that I have favorable interactions no matter where these hydrogens are pointing. If the hydrogen is pointing up and forward, then these two just simply have to be more electropositive to make it work. If we have a case where the hydrogen is pointing up and towards the right, then these 2 molecules, or these 2 hydrophilic molecules, are going to have to be more electropositive. In a third example, if I have my central water molecule with hydrogen pointing here and hydrogen pointing here, it's obvious that these 2 will have to be more electronegative so that the hydrogens can be attracted. And then the other remaining 2 are going to have to be electropositive for the 2 lone pairs of electrons on the oxygen. So hopefully that makes sense. If not, we're going to go through a few more examples. So let's take a look at this in a bit more detail. We now want to figure out the multiplicity of, or basically the number of possibilities of the 2 hydrogens to orient themselves. So in this case, we're assuming there's just water molecules at the corners of the tetrahedron. So I've drawn the previous diagram wasn't the greatest because it was just all red, but now I want to make the difference between oxygen facing and hydrogen facing water molecules. So I take a look at my central water molecule here, and I want to figure out its multiplicity. And that means how many possible configurations can it have in a hydrogen bonding network. So if I have the big purple circle as oxygen and the smaller lighter purple circle as hydrogen, we'll be able to differentiate which part of the water molecule is facing the central water molecule. So looking here, I have a tetrahedron shape because I know that every water molecule can form up to 4 hydrogen bonds. So I have 1, 2 in front, 1 water molecule at the top, and a water molecule at the back. This forms a hydrogen bonding network. And the water molecule in the center is fully satisfied. So looking at this, my question now, in order to figure out my value for W, I'm trying to find out how many ways I can orient my central water molecule so that everything works out. So option number 1, I can have my hydrogen facing this way, or this corner. I can have my other hydrogen facing this corner. Because each of these corners are water, I have a choice of either twisting them around so that it's oxygen facing the central water molecule or hydrogen facing the central molecule. So if hydrogen is here, pointing towards this, and hydrogen is positively or electropositive, then this has to be electronegative in order for a favorable interaction to occur. So that's done, and that's possible. Now we have another hydrogen facing this corner, which means if I reorient my water molecule so that oxygen is facing towards the center, there's another favorable interaction here as well. So that means my central water molecule is aligned so that the 2 hydrogens are facing side 1. So I've labeled this side 1 of the tetrahedron. If I take a look here at my other option, what if I twist this central water molecule around? I twist it around so hydrogen is facing up and towards the right. That means if I just change these 2 hydrophilic, or basically water molecules, so that oxygen is facing these hydrogens, it works too. There's no problem. It's also favorable interactions. The remaining 2 become hydrogen, and they're all favorable. But now, my hydrogens are facing side 2 of the tetrahedral shape. So if you start reorienting the water molecule in different ways, you'll eventually find out that it doesn't really matter what direction it's facing. It'll have preferable, electrostatically favorable interactions for every single side that the 2 hydrogens are facing. So that means 1, 2, 3, 4, 5, 6 sides of the tetrahedron means 6 different possibilities for hydrogen bonding and hydrogen bonding configurations of the central water molecule. So by observation, I can say W is equal to 6 because there's 6 different configurations possible. And that's something that you'll have to know how to do for assignments and also exams. And it should also be something that you should be able to apply to not just a tetrahedral shape, but to any random molecule in different 3D structures. So if I have W, then I should be able to calculate entropy as well. So to calculate entropy, I just calculate the Boltzmann's constant times ln of the multiplicity, which we've discovered to be 6. So if there's ever a question asking you about the entropy involved with the configurations of a central water molecule, then you'll know how to solve it because you'll be able to observe and determine what W is. So now let's go through hydrophilic and hydrophobic molecules. Hydrophilic substances are those that are going to dissolve readily in water. They're composed of ions or polar molecules, which means they're going to attract water. So that makes sense and that's logical. In fact, water molecules are going to come around, surround each hydrophilic molecule, or basically charged molecule, and carry it into the solution. The example here is of salt, or table salt, dissolving in water. If you're ever asked a question about table salt and why it dissolves in water, a good answer would be that the table salt is composed of sodium and chlorine ions that are positively or negatively charged. The water molecules are going to come in, reorient themselves, trap these ions, and then carry them into the solution through the hydrogen bonded network. Meanwhile, hydrophobic substances contain a majority of nonpolar bonds, making them insoluble in water. So molecules without charge are not going to attract water molecules. So the changes that these substances, or the chances that these substances will join the hydrogen bonded network are going to be really slim. So there's not going to be any interactions with the water molecules at all. There might be a reorientation of the water molecules to make space for them, but they're not going to change or join the hydrogen bonded network because they're not charged. There is something special about hydrophobic molecules though. It's that the majority of them contain carbon-hydrogen bonds, so they're called hydrocarbons. So let's test our knowledge about interactions of hydrophobic molecules in water. What happens if we introduce an oily hydrophobic substance inside a hydrogen bonded network? So what if I force an oily substance inside this hydrogen bonded network? What is going to happen? So my question is it going to break the previously formed hydrogen bonds or not? And the answer is actually B. So, it doesn't break any previously formed hydrogen bonds. And why? The answer actually is a bit confusing. You might have to read it a couple times over, just like I did before. If we think about entropy, it might make sense or not. These next few slides are going to take some time for everyone to wrap their heads around. So if things don't make sense, please discuss and ask questions. So the idea is that when we introduce an oily substance inside water, it's not going to break the previously formed hydrogen bonds, but instead, the water molecules are going to reorient themselves around the oily substance to remain fully H-bonded. So that in itself does make sense, but we're in a course that really focuses on entropy, and before I said that entropy has to do with the amount of disorder in the system, and that there's a law of increase in entropy, so we always want to increase entropy. And that's the same with these water molecules. They want to increase entropy. The only problem is when we introduce a hydrophobic substance, they're going to reorient themselves around the hydrophobic substance, and that action actually decreases entropy because it increases order. So that now doesn't make as much sense. So the idea is that your entropy is going to decrease for your collection of water molecules. But from before, I always said that the system, or any isolated system, will always tend towards a state of higher entropy. So although it might be counterintuitive right now, the key phrase here is isolated system. So an isolated system actually refers to the individual water molecule. So if the hydrogen bonds break and the water molecule is now exposed to a hydrophobic substance, so remember that tetrahedral, the purple diagram that I had before? If I replaced one of those corners with a hydrophobic substance, it means that the water is not going to be able to configure itself in as many different ways, because that corner is basically a null corner. It won't have any interactions. So in this case, the entropy of each individual molecule is going to decrease if the hydrophobic substance actually broke the hydrogen bonds. And that is way more unpreferable than having the collective entropy of all the water molecules decrease slightly. So in terms of summarizing this, if the hydrogen bonds break and the water molecule is now exposed to a hydrophobic substance, it will no longer have W equals 6, but maybe W equals 3. So that's going to affect every single water molecule, which is not as good as just having a tiny sacrifice to decrease the collective entropy without affecting every individual entropy for the water molecules. Now we're going to take a look at what happens when your water is cold or hot and you've added some hydrophobic solute to your mixture. So in A, we have a hydrophobic solute that's about to be dropped to a hydrogen bonded network here. In B, we have a reorientation of water molecules around that hydrophobic substance. And in C, we have less of an order in hot water. So we're going to take a look at what's happening for each. And let's start with cold water. So in cold or room temperature water, the water molecules will almost always reorient themselves to remain fully hydrogen bonded. That means their individual entropies can be maintained. Unfortunately, the sacrifice, as we've mentioned before, is that they become more structured and they're going to have less entropy as a collective. With hot water, things are a little bit different. The water molecules are now heated and they have more movement, which already disrupts the hydrogen bonds. And so the entire system becomes less structured and therefore has higher entropy. And it's already hard enough to maintain a network of hydrogen bonds. So the effect of trapping your hydrophobic solute isn't as evident here. And because your whole system already has a higher state of entropy, it's already a preferable configuration to just have your hydrophobic solute mixed in with your hydrophilic molecules. So to follow up with what I've said before, in terms of what happens if you add some sort of oily substance, we can finally do a detailed analysis of hydrogen bonding geometry again, but replace the back vertex with some oily thing. So it's a hydrophobic molecule. It means that there's not going to be any interactions with it with any part of your water molecule. That means none of it's going to face the back. So all of our possible configurations for H are going to be limited to these three vertices. So that means I have one configuration for side 1, another configuration for side 2, and another configuration for side 3. No matter what, there's going to be one side that's null, so your lone pair of electrons can only interact with the remaining vertex that isn't an oily substance. So in this case, I only have 3 preferable interactions with the hydrogens, and that means our multiplicity is now 3. And because it's 3, it means that your water molecules will prefer to reorient itself so that it doesn't have to end up with W equals 3 for every single water molecule. But there is one bright side to all of this, especially for the water molecules. It's really sad that they have to lose some entropy by reorganizing themselves. It's even worse if there are multiple hydrophobic substances being added. So imagine adding a whole bunch of hydrophobic substances here, like these little chicken feet structures. That means your water molecules are going to have to keep reorienting themselves and continuously keep getting more and more organized and more ordered. So they're going to continuously lose entropy. And that's not a good thing for them because every system will tend towards a state of higher entropy. So in order to fix this, they actually do tend toward a state of higher entropy by grouping all of the hydrophobic molecules together. So the more hydrophobic groups you add, the more your water is going to force those hydrophobic groups together and minimize their disruptive effects on the hydrogen bonded water network. And together, these efforts actually increase entropy and can therefore prove that all systems tend towards a state of higher entropy. So as a summary of this section, weak interactions are going to play a crucial role in everything. I wanted to present some constants before I finish with this section that may be useful for some upcoming assignments. And that would be Boltzmann's constant here, which is 1.38 times 10 to the negative 23 joules per Kelvin, or all this. And if you have a temperature at 300 Kelvin, then 1 kBT is going to be equal to 0.6 kilocalories per mole, or 1 over 40 electron volts of energy. We can then assume some known values of 10 electron volts for the energy of a hydrogen atom and 1 electron volt for the covalent bonds between atoms. So these are some values that you can just use if you were trying to model something, especially for assignments. So now let's go through some applications of hydrogen bonds in macromolecules and why they're so important. So we're going to be going through each of these in a lot more detail throughout the whole course. In fact, we're focusing one entire unit on each of these macromolecules, and you're going to see hydrogen bonding over and over again. So it's very important that you understand where it plays a role and also what types of configurations it can have in relation to different molecules around it. So we've learned about hydrogen bonding network in water. We can extend that knowledge now to different macromolecules. So if you have a long or large molecule in water, it should be able to form hydrogen bonds with itself, right? So technically, this long or large molecule can start to fold to have preferable hydrogen bonds for a specific configuration. And we can actually model a whole bunch of different things just by using hydrogen bonding. You can even have models to help predict hydrogen bonds with neighboring molecules. And it doesn't always have to be water. It just has to be hydrogen bonding between an electronegative region and an electropositive region. So we're going to extend that knowledge and apply it to all other types of, all the types of macromolecules. So the next few slides will basically just go through an example of where we can see hydrogen bonding in different macromolecules, and basically where we're headed in this course. So one example is DNA. We have hydrogen bonds between the different DNA base pairs. So you have 2 hydrogen bonds here between adenine and thymine. You have 3 hydrogen bonds between cytosine and guanine. And so these represent the different pairs that are possible because only 2 hydrogen bonds can be created between A and T, well, 3 hydrogen bonds are created between C and G. And it's because of this that we have this twisted ladder or double helical structure of DNA. We're going to take a much closer look at this for the second half of the class as well to actually see why the DNA forms a helical structure and why all of those energies are preferable. And not only that, we can also have hydrogen bonds in proteins that'll give us a certain configuration. So as you've probably learned in either some of your bio courses or Physics 280, hydrogen bonds can play a role in the formation of an alpha helix or a beta sheet. So here I have an alpha helix, and we're going to use a very similar model to predict its folding towards an alpha helix, just like a DNA helix. And for a beta sheet, you start to have hydrogen bonds that are between peptides in different strands, and that forms a sheet instead of a helix. And so depending on what types of preferred hydrogen bonds are present, that's going to tip the scale towards a more favorable configuration for a protein, whether it turns into an alpha helical structure or a beta sheet structure. And of course, my favorite hydrogen bonds are definitely going to play a role in lipids too, which we're going to focus on in the latter part of this course. It leads to an entire discussion of energetically favorable and unfavorable configurations of lipids that basically can kickstart different types of lipid self-assembly. So depending on hydrophobic and hydrophilic interactions, you can have planar sheets. You can have it slowly form into a vesicle, or you can have that planar sheet, which by itself is not favorable. You can have it rest on a substrate and have that interaction be favorable as well, if you know what kind of lipids are at the bottom and what kind of interactions they're seeking. So as a summary for this entire chapter, what kind of important things have we learned? First, we learned that chemical bonds and weak interactions are present in everything that we look at. We know covalent bonds are the strongest type of bonds, and then hydrogen bonds come next, and they're the strongest intermolecular force. Next, we really focused on the water molecule. So the water molecule is extremely unique. Hydrogen bonds are going to allow it to have a whole bunch of different binding properties. There's also its tetrahedral hydrogen bonding structure for your hydrogen bonding network. That is something that I would want you to review because it's very important for this course. Afterwards, it's going to interact differently with hydrophilic or hydrophobic elements. Remember, with a hydrophilic element, there's going to be a higher multiplicity or more configurations for your central water molecule, because I can choose a hydrophilic element, which technically is a polar element, to spin around and have the electronegative or electropositive region interact with the water molecule, whereas for hydrophobic, there's nothing for it to interact with. So those are key things to remember. Next, we went through a few examples of where hydrogen bonding was crucial in the configuration of macromolecules. So the primary examples are in DNA and protein folding, and we're going to spend entire chapters on those as well.